And what I've decided to do so that I can get to my punchline is I'm going to tell you a little bit contrary to what I had planned to exactly do, is I'm going to give you a number of results. Okay, so I want you to bear with me. We're going to do the results. And then at the end, we'll use the last part of the period to basically describe at least the big steps of one of the proofs, and I will explain why I want to do that. And in that board, I will try to, so this is going to be one of those stories where I present a result and it proves something, then we prove something better, and then we prove something better. So if my artistic skills allow it, I will try to draw the 3 steps little by little in that board, okay? Okay, so, but no promises. Actually, when I taught this class, one of my students did these beautiful pictures where they were islands and things of, yeah, well, I tried to make a mental picture, but it did not happen. Okay, so I don't guarantee a pretty picture, but, I'll try to make a picture. Okay, so I remind you, because motivated by the density estimates on perimeter minimizers, we decided to describe this class. So this is an A. C of A R0 was the set E, is the set of the class of sets in Rn, which are locally finite perimeter, and such that the support of the perimeter of the measure is the boundary of E, and the perimeter measured is outforce regular up to scale R0. And I remind you, E, this is a long parenthesis to have to close, for every x that belongs to boundary of E and every r between 0 and R0. What this means is that the perimeter measure over R to the n minus 1, remember we live in R, is CA, and CA minus 1. Okay. Don't hesitate to stop me if you have questions. Okay? So we had proven, we had stated something that looked almost like a compactness statement. So I remind you what it meant. Theorem. If we have a sequence of sets in here, and the reason I'm writing it is because we will use it, actually, we really use it a lot. We anchor the sets so they don't run out to infinity. So we put 0 to be in the boundary. How do you do that? Well, you translate them so they're all there. Then there is a subsequence such that the following things happen. Okay? So the E sub nk converge to a set E of locally finite perimeter. The mu of E and k's converge weakly to mu. I remind you this is the vector valued measure. To mu of E, sorry. Mu of E and k converges weakly to mu. This is a non-negative radon measure. Okay? And so, moreover, so I remind you, this is a vector valued measure. This is another measure. This one here, the non-Alford's regular up to scale R0, and there's a relationship between these two measures. The total variation of E is less than this one, and in general they're not the same, and that's one of the problems. And there were 3 more statements, and we're not too stressed about them. I'm not going to write them. Okay? Questions? So this is roughly a summary of the last 40 minutes of last time. Any questions? Because I'm going to go from there. Okay, so as I had said, what we want to show is that just on this class, if the unit normal is not doing crazy things, the measured theoretic normal is not doing crazy things, I have a lovely representation of the set. Okay, so how am I going to measure the behavior of the unit normal in terms of the oscillation in L2? I'll write that down. And the first thing I'm going to write down is I've been dealing with balls. For the second now, I'm going to deal with cylinders. So let me, okay, so I'm going to give a name to my cylinder. So let me, if I have x naught here, okay, r here, and this is the vector nu. So we all agree this looks like a cylinder of base r and height r, correct? Need to name it, because I cannot draw it every single time. So this will be the cylinder of center x, radius r, with direction nu. And maybe let me leave it like that. Let me not introduce necessarily more notation, I am sure. Once I need it, I'll introduce it. But you see who it is, correct? OK, perfect. And now I want to introduce a very important quantity. So if we were looking at perimeter minimizers, this is the key quantity to control. Turns out that here also. OK, so we are going to talk about E, excess of the set E, one of these guys over here, at the point x naught at the radius r in the direction nu. Bless you. And nu belongs to Sn minus 1. So this is a unit vector. OK? And who is this? Well, the excess is, remember, is 1 well, over Rn minus 1. I'll explain why. Bless you. Hope you're not allergic to me. Because x naught r nu. And we are going to the oscillation of the unit normal. So is the oscillation, I want a quantity. Remember, this unit normal is only defined almost everywhere. So it's not even a nice function. I cannot tell you, OK, look at it and look how it changes with respect to this one. So I can only do it in an L2 sense, for example. And I'm going to see how much it oscillates with respect to these. So I look at nu of E minus nu square. I divide by 2, so something very nice happens in a second. It's one of those magic moments that you don't know why you put a 2 there, you'll see. With respect to this measure, okay? The perimeter measure. That's the excess. So what exactly I am saying? I'm saying, remember this guy changes like r to the n minus 1. So in some sense, this is roughly, let me do a proof by illustration. I hope we all agree that if I have this cylinder of radius r, I can stick a ball of radius r inside it. And that my cylinder is contained, do you see the yellow? And that my cylinder is contained in a ball of square root of nr. The specific numbers don't matter. The important thing is it's comparable to r. So cylinders contain balls. Balls contain cylinders of comparable radius. So this thing here is roughly the average of the oscillation of the unit normal with respect to this guy over here. Okay? So maybe I should draw a picture. So this number is always less than 2. Okay? So this is going to be always a finite number. That's not the point. But let's for a minute, let's do 2 examples so that I drew, so this picture, and maybe I want to make it pointier, this one, okay? The point where I'm standing is here, and the point where I'm standing is here. You realize here, it looks like the unit normal to this, if this is my set. Well, it changes a little bit, but it doesn't change that much, correct? I mean, it's more or less. Like, on the other hand here, and so when you're integrating in some sense, sorry, what is happening is that these guys are canceling these guys. And if I put a nu there, well, it's going to, you know. So the oscillation here will be big. The oscillation here will be small. Okay. This is not a proof of anything. But at least at nice points, the oscillation is small. What we want to prove is that if the oscillation is small, we are in a nice point. Okay? Question about this quantity is going to play an important role in what comes next. Okay.
One question.
Yes? Go ahead.
Are you dividing by Rn minus 1 because it's a surface measure? So it's actually n minus 1 dimension?
Because this guy grows like that. Okay? I could have divided by mu of that, but then, yes, it would have looked more like an average, but then we would have created royal pain. So you know. And since all the constants that I've obtained, for me, the constant 2 or the constant 17 are roughly the same. It doesn't matter.
So is this going to be like, are you covering the boundary with this bulb and then putting the?
Well, it turns out I would love to do that, but it's not true that I am interested on the points when this is things small. Okay? So what I'm going to be able to say, if this number is small, something good happened. And yes, at some point in one of the applications, somehow one of my hypotheses is that this is small everywhere, because I start with a statement that says the oscillation of the unit normal is small on all balls of a certain radius, therefore it's small in all cylinders, and then I apply. Why did I choose the cylinder? So this, I'm going to make a comment that the first part of the comment, that even though everybody will most likely understand the comment, it might only have a second meaning to some of you. So one is one of the big, this funny problem we're looking at, you will see, being flat with respect to this plane, so in this picture, is exactly the same thing as being flat if I had drawn my cylinder twisted, okay? Because this problem doesn't see the rotation, okay? If I'm looking at a set, and I'm looking just simply at this type of flatness, it's the same thing if the set's standing like that if the set's standing like that. For some of the problems, and in fact, one of the motivations we had to do all of these, I mean, I told you one of them, but let's say the true motivation to do one of these was to try to understand what happens with a functional. So we're looking at perimeter. Perimeter is something that doesn't change with rotations. We were very interested in a functional where being that is not rotationally invariant. And then being flat with respect to somebody is not the same as being flat with respect to somebody else. And we still are trying to understand what that means. But here, so what I'm going to do is I'm going to cover things where my set at the points where I have something like this. Remember, these sets are ugly, but I'm going to say that when this is small, something nice is happening. Okay? Let me do a tiny bit. We're going to do, I'm going to explain 2. Okay, so let's expand. This is, when I expand this is 1 almost everywhere. So this is a 1. This is a 1. So I have 2 minus 2, the inner product. The 2 disappeared, and this is the same thing. Let's see, of x naught r nu of 1 minus nu e nu d nu e z. Did you have time to do this last? Yes or no? Okay. So why did I write it like that? So we're not going to have time to do it, but remember, the first day on Sunday, you look at a graph. So imagine that this was a graph, and what I would like you to try to understand is who on earth. Let's imagine the set E is the area below a graph, okay? Who, of a Lipschitz function, of course, sorry. Who is this quantity? Well, this quantity happens to be the same thing. So I'm going to draw my picture. Let's imagine this is my cylinder, okay? So this is my x naught. This is R. I have a lovely graph. And when I look at that quantity, so here, the first piece is, so first of all, we all agree that this is greater or equal than 0, correct? And this is a, so the first piece (1 over Rn minus 1 C of x naught R nu d mu of E is going to be this piece. Okay? The length or the surface of this piece. And then, and unfortunately we don't have time to do it, Rn minus 1 C of x naught R nu. I leave it to you to convince yourself. You know what the nu of E is in this case. You did it on Sunday. You know what mu of E is just the surface measured. And in this case, when you look at that, I'm going to write it just because that is this, the length of this. And so what does this quantity, this funny quantity that measures the oscillation of the unit normal, also we all agree that this is the shortest, this is the minimizer between here and here. So I am comparing the minimizer to the thing that I have on top. And if this thing is small, in some sense it tells me that this cannot be curving as much and is relatively flat. Okay? That's why this quantity works for the minimization problem, but okay. Okay, so, questions? Yes?
Are you saying something like if something is a perimeter minimizing, then it also minimizes this oscillation of the normal? Like, are you saying that they're equivalent problems?
No. What I am saying, if I am, so the thing is when I only have 2 lines, it's relatively easy. I mean, when I only need 2 dimensions. But what I am saying is when I am perimeter minimizer, at those points where I have a small oscillation of the unit normal, I am very close, in some sense, to being the flat thing. And the flat meaning, the plane. And then once I'm very close to being a flat, what I am able to do is I'm able to construct a competitor that that improves what I had and is the graph of a more regular function, a harmonic function. And that's how it goes. It's not true that all minimizers are graphs, I mean, at every point. But the relationship, and I am not looking, because being a minimizer is almost infinitesimal, and here is at the big scale what happens, okay? But yes, it has to look flat in some sense, at the good points. Okay, so let me tell you, so I said I promised to say, so this is the first lemma. So we have this funny feeling that if the x is small, at least from this picture, this cannot wiggle too much. This has to be way flatter. I mean, it doesn't mean it has to be here, but it has to be, here I've added too much mass. So first lemma, or first theorem, is called small xs. Actually, in fact, they all could be called the same, but but it's one. So small xs implies, I'm going to put here flatness, but this is in some sense quotations, measured flatness. You'll see what I mean. It's not, is that the next one I'm going to call small excess implies flatness, and so to distinguish. Okay, so remember, even if this is complicated, I'm going to draw my first picture there. Given a constant CA bigger than 1, and T0 a number between 0 and 1, there exists a number. So because of this, the type of analysis required to know what my numbers depend on, otherwise I might end up chasing my tail and proving nothing. So there's a number that depends on the dimension, the place where I live, the alpha constant, and this mysterious number T0 that I chose, but this number is small, okay, such that if E belongs to C of A of CA are 0, for some are 0 bigger than C, and for some x, okay, for x that belongs to boundary of E, and some new, I don't know which one, the following thing is true. The x's above of E at the point x0 at the radius r0 in the direction nu is smaller than this mysterious number, then 3 things happen. Okay, so let's do, to simplify life, and so I don't have to introduce so much notation. We're going to do something starting now. Okay. From now on, in this box, nu is E sub n. Okay. Q sub x. Q sub x. Well, let me do something. X0 is going to be 0. Okay, so I don't have to. And Q sub x is the projection, so is the height. If this is a point x, Q sub x is the height. That's the inner product between x and E sub n. And let's remember, this is just simply xn. Okay? So. And so when I write this here, maybe I should have written it like that. It has nothing to do. It has nothing to do with this, but it makes what I'm about to write way simpler. Okay? So, yes?
I don't totally see, like, why is this difference of these lengths?
I'll be very glad to explain that to you. That's it's a computation. It's a computation I had planned to do, but what I wanted to say is, if you go back to Sunday, if you were here on Sunday, where you wrote what the unit normal, if you have a graph, what the unit normal is and what the surface measure is, and you just plug it in, you see that that's what you have. Okay, so if it's general, is way more general. It's not only for the cylinder, it's for any piece. But if you write it in the cylinder, you'll be able to see it. Okay, that comes out. Okay, so if this happens, so what am I assuming? Then 3 things happen. So let's draw the cylinder. So what I am saying is that the unit normal here, and of course all my pictures are smooth, so it's kind of annoying because apparently you don't see that much. Maybe I should anyway. So then. Here is what happens. Let me double check. Let me write it correctly. I don't want to mess up these. Part 1. Q of x, which means simply xn, is less than T0 R0 for every x that belongs to the boundary intersection the cylinder and I am going to do something. I'm going to put a 2R0 here, and I'm going to put a 2R0 here. I'm sorry about that. It just makes my life simpler. And I'm not lying that way. 2. So I have to shrink the cylinder. If I look at the Lebesgue measure, so of the set X, that belongs to C of X naught, R naught, E sub n, intersection the set E. I know, I haven't finished my sentence. And I also look at this set. So the reason I'm not writing it is because I want to draw it before I write it. I think if I show you the picture and then I write something, it's cleaner than, OK. So I'm looking at the points in E. So remember, this picture, E sub n goes up. I am saying the axis with respect to something that's going up is small. It means that the unit normal of this guy better kind of should be looking that way, okay, to the top. Therefore, if the unit normal is looking to the top, you expect the set to be below, correct? Somehow. So that's what D says. So if we look at the points where Qx, think of it at xn, is bigger than T0 R0, something happened. And if we look at the points here in the complement, I'm about to draw, so please don't. Just give me a minute so something happens. I know I haven't written what happens. OK, so let's see what on earth my picture is saying. So I start here. I should have. You see, my artistic design is already messed up. I'm going to draw the cylinder. That one I can draw perfectly fine, mostly. OK. I'm trying to do so. First statement tells me the oscillation is small. Then when I draw the boundary, I have to draw it. If this is R0 and this is R0, my boundary is stuck in the place where xn is bounded between, the height is bounded between T0 R0 and minus T0 R0. Correct? That's what this says. This one over here. Xn is between that. So where is that? Well, I put all the chalk here. So this is T0 R0. And so my boundary is stuck here. OK? So the first thing I can prove, and of course in this picture you're going to tell me, oh, but you can say, well, the first thing I can prove, bear with me. I am not saying that that's the only thing I had proved, but that's the first thing I can prove. The first thing I can prove is that my boundary somehow lives here. And you see, this is where I screw up my picture, because my student was able to draw this beautiful ocean and then the islands, and I'm not going to even try because I know it's going to be a disaster. So think of this as a two-dimensional picture, OK? That's the first thing. So my boundary is in here. Besides that, I don't know what happens here. But what number 2 is trying to tell me, once I finish writing what it says, is if I look at the points that are above. And I'm going to do something here because.
Did you make it on purpose that it says your last name?
Huh?
Oh,
Where does it say? Oh, no. OK, I'm going to correct. It's funny, nobody had remarked that. OK. Anyway, and so what does this one say? What I want to say is that above, which is here, OK, this one has to be 0. I mean, of course, in the picture, there's nothing. What are you talking about? Well, yes, I know, but that's not what I can show. So this is what I can show. And then when I look at the complement, so this is 0. So roughly speaking, E lives here, and E complement lives here. Okay? And at this point, I only have done it in math. So I only know, so if you want, what do I know? I don't know that there might be pieces of these that happen to be here. So pieces of E complement and vice versa. We're going to get rid of that problem in a minute. But at this point, in the first stage, we cannot do that. OK. Any questions? And if I have a minute, I won't have a chance to prove the theorem. But I will hope to have a minute to illustrate how one proves something like this. Is it proof by contradiction? Yes?
I have a question. How does the cylinder know up from down? Is there, it still always point up, right, in the cylinder?
I always chose the thing pointing up, OK? And remember, I chose nu of E. If it were C1 is the outward pointed normal, that means, OK. So if this cylinder happened to be pointing like that, you just stand on your head, and then it looks up. Yeah.
Is this saying that there exists this E sub n?
No, I'm starting by assume there exists E sub n. So, but that brings us to a good point. This is a, you have to be mad about empty statements. So my statement says, if there is a guy like that, then blah, blah, blah. And I'm going to actually say, if there is a guy like that, even more nicer blah, 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 occur. But you then ask yourself, but does that exist? But remember, the points in the reduced boundary are the points that are density points for the unit normal, where this average goes to the unit normal. Okay? In my class of objects, the boundary corresponds to the topological boundary. Therefore, almost all the points, there's lots of points in the reduced boundary. Okay? The reduced boundary is big. Okay? Therefore, I'm going to have lots of points where that happens, so I don't have to worry about that. Now, the issue is at what scale it starts happening. But that's an issue for later on in life. Okay, it's not going to be part of this week. Okay. Okay. Any other questions? Okay. So I am going to remember I said x naught was going to be 0 in. I'm not going to change my set E for a minute. So I'm going to shorthand this notation because I'm running out of time. So I'm going to call these En, x naught, 2R naught. And it will be En of the point and the thing. Now, the next lemma tells us the following. Actually, the next theorem tells us that that picture that I have there is close to reality. So theorem. I think, and let's, in terms of what you believe, we could all believe that actually this is going to have, when I say that this has measured 0, we're going to believe, it's easy to believe from the picture that we can show that this is empty and this is empty. But T0 is this awkward thing that I chose. And I am actually interested in knowing exactly how flat this is, okay? How tall this is. And that's what this tells us, height bound. And if you want, what this should call height bound is, what really this should say is small x's implies flatness in a quantitative way. That's the shorthand. So given n greater than 2, a constant bigger than 1, there exists a number, an epsilon that depends on n, and on CA, we're going to call it epsilon. It's going to, of course, be, it's going to be small. You'll see in a second. It's going to be smaller than that number in some sense. Small. So this is a small number. So, and a constant. This is bigger than 1, such that if E belongs to A, CA, 2 are 0, so same thing as there, and En, remember I'm shorthanding that to R0, is less than epsilon, then the following thing happens. Remember, I'm choosing x naught to be 0 just because it makes my life easier. But so then 1 over R0, I'll draw this. Please bear with me for a second. The sup. So I look at the height. I am going to look in a smaller cylinder. I always need to kind of my cylinders a little bit smaller. So really poor board technique. You'll see because I'm about to put the punchline in the wrong place. So the height (1 over R0), the sup of Qx, where the x belongs. I've shrunk the cylinder a little bit. That's because at the edge I always have problems. En, intersection the boundary of E. This number is less or equal. So from that theorem, I know that if I choose my epsilon small enough, depending on T0, that if I chose a small T0, then I could make it small, but I don't know how they quantify. Here it tells you precisely. This is less than this constant, that one that I put over there, times E of n of x naught 2r naught to the power 1 over 2 n minus 1. So this is telling me that if I started with a small oscillation, this thing didn't do wild things. In fact, in my smaller cylinder, okay, I know exactly what this height is. And the height here is comparable to En of x naught 2r naught 1 over 2 n minus 1. So I have a very, very, very precise estimate. Okay. And I might not look as much, but let me explain how these things work. You start, I mean, as I was pointing out, how am I going to get points where I have a small axis? Because I look at a point in the reduced boundary. I look at a point in the reduced boundary. This is going to tell me that point is really flat. Okay? Because look, this is what, look, this is a scale invariance, so the flatness is really small. In a minute, I'm going to tell you then what do you do next. So what you're going to do if you had a perimeter minimizer is you're going to show that now you are really able to look in there. So let me draw you a picture of something that's really flat, but it's not very pretty. Because I'm going to draw it here because I can't cover it again. So if I had a snowflake which is very flat, so of course the unit normal is not good here, but let's imagine you're thinking, oh, I already got to where I wanted to know. I can draw something that's very flat but it's not good, but now I'm going to use again what I have, the fact that the flatness comes from the smallness to show that actually that piece over there is really, really nice. Okay? So, and this is finally, finally I'm getting to the uniform part of the title of the class. Okay, so let me, better later than never, we say in Spanish. So let me write the last part, and then I'll give you, I have very short time, I'll give you an idea of 2 or 3 applications for this. Okay, so questions? Yeah.
In your picture for the E complement and E, so is E complement corresponding to the Q of x less than negative P of R naught?
So no, the Q of x less than minus C of R naught is the E.
Is the E? Okay.
Yeah, because somehow it's the outward normal.
Oh, okay.
Okay? I know.
It's okay.
The thing lives under. It always lives under. Okay? Any other questions? Okay, so let's see. And so all of these, in the case of a minimizer, this is how you classically prove that minimizer I'm following. So if you were ever going to go read how you prove that perimeter minimizers or perimeter almost minimizers are regular almost everywhere, this is what you will do. But remember, I wanted to use this in a setting where I don't have any perimeter minimizers. I only had objects in that class that I described. So here is what we're able to prove. And yes?
Before without any other assumption, are these any smooth or are they any or not?
You're about to see. You're about to see how smooth you can expect them to be. And so since I know who you are, yes, they're super smooth. They're going to be Lipschitz. No, I cannot expect them to be anything better than that, okay? But if you think of it, if I rather than having chosen a set of locally finite perimeter, I had chosen, what I'm asking is I'm taking an Alford's regular measure that happens to be a perimeter measure. And out of that, I'm getting some sort of regularity, which I'm about to state. But an Alford's regular measure could be the Hausdorff measure of the four-corner Cantor set where you still have. So, so these qualitative assumption that you are the boundary of a set of locally finite perimeter and that the Alford's regular measure is the perimeter measure is giving you a lot of information. Okay? So hopefully the next thing will answer your question. Okay, but if not, ask me again. Okay, and so theorem Lipschitz approximation. So remember how I had said that uniform rectifiability says that uniform rectifiability meant that instead of being a countable union of Lipschitz pieces, each ball was a big piece of a Lipschitz graph, and it didn't need to be a big piece. It was a piece of a Lipschitz graph. So here is what we're going to say. So under the same, so for every n greater than 2 and for every Ca bigger than 1, there exists a C1 that depends on Ca and an epsilon 1 that depends on. Why am I spending time doing the dependence? Because if you ever want to go and try to prove these things, since this is all proved by compactness, you need to know what depends on what, otherwise it's a problem. Okay. And delta 0. And here I'm going to give you a little bit more information that you may want, but it might be useful to somebody, such that if I take a set in this class, okay, Ca to R0, for some R0, and of course I have to start with a small oscillation, x0 to R0 is less than epsilon 1, okay? So this is epsilon 1, C1, I'm going to drop the dependence so I have. Then, and for x0 that belongs to boundary of E, I define mu is the cylinder of centered x0, R0, E, intersection boundary of E. I define M0, the set of points Y that belongs to M. So I'm assuming that the oscillation with respect to E sub n is small. I look at the cylinder and I look at the Y's that belong to M such that the oscillation at those points with respect to S, so in a small, we look at these points. So S is between R0 over 3 and 0. You look at the points where the oscillation with the unit normal at the big scale is small, Now I'm saying, look at the points with the oscillation in here. With the oscillation with respect to E sub n is small somewhere else. You might tell me that set is empty. I think it's a fair assumption at this point. Let's see what happens. And what this says is exactly the opposite. Most of the set is that. And that would be so there exists U, Lipschitz. So U goes from R-1 into R, Lipschitz, with the Lipschitz constant. Hopefully you remember Sunday. Lipschitz constant is less than 1. The height of this Lipschitz function, the height of this function are 0 in Rn minus 1 is less than C1 En of x naught R naught 1 over 2 n minus 1. If you consider the graph of these functions, so these function, the points of the form u of x En, okay? For x that belongs to d of R0, who's d of R0? I need to draw, I'm not sure. There was green. So d of R0 is this, the flat piece, d of R0. So it's green. Is the disk on the flat, is the disk on the ground? Okay. So if you look at that, here is what happens. So I'm going to have to enlarge this picture because now you're not seeing anything. But what we have is, I start with this piece. I build a Lipschitz function. I haven't told you anything about the Lipschitz function. I have a graph, and what the next thing says, the graph is not very high, is that M0, this funny set is inside M intersection. The graph, well, that's not that much because if M0 is empty, I'm saying nothing, so that's useless. And moreover, the difference between the set M, which I chose, and the graph over, remember, they all live in over R0 in a cylinder of radius R0. This thing is less than C1 En of x naught R naught. And moreover, so this function, my Lipschitz function has Lipschitz constant less or equal than 1. But on the other hand, if you look at its gradient, so the Lipschitz constant is roughly the soup of the gradient. So tells you the soup of the gradient is less or equal than 1. But if you look at the L2 norm, so this is, I'm going to call it, you're only differentiating on the plane. I'll draw a picture in a second. This is less or equal than, which constant did I put there? Sorry about that. I put C1 everywhere. C1 En x naught R naught. Okay. What's the gradient prime? Remember, I live in Rn. So these means I only have d dx1 of u to du dxn minus 1. Because remember, so gradient would have been if it had been in Rn. So gradient prime is, remember. So let me draw the picture, OK? I'm going to draw a picture. Bear with me. OK? What on earth have I done? I started, so now I'm enlarging my picture. I started with something. Forget that the silly cylinder is not, I don't want to draw it anymore. I started with something that was stuck between two cylinders, but it could have looked like that. Okay? And maybe there were wiggly things here that I was not able to see. Yes?
What are you taking the interval with respect to?
Oh, with respect, I should call this dx. Dx bar, where a point x is a point of the form x bar xn, and x bar are the flat components. Okay? So I have this guy. Here is Rn minus 1. Okay? Here is the n. And the first thing told me, the oscillation of the normal is small. If the oscillation of the normal is small, it means that most of my set, that the 1 and the 2 tells me the set lives mostly here, and the complement is mostly here. Then we said, no, it's actually really squeezed in between. So if this is x naught, and now look what I have done. And this picture is not quite correct. I'm going to need to make it flatter. There we go. What this is telling us is the following. Every time my oscillation is small in this ball, when I look in this ball, if this is R0, I am seeing a graph. So maybe this is too high, so I don't do that. This one. So this thing. So there's a Lipschitz function. The Lipschitz function might do this. But the red thing is gamma. Gamma, here is the function u. And so gamma is the graph of u. U has Lipschitz constant less than 1. So that tells us u of x bar minus u of y bar is less than x bar minus y bar. The difference between this set, so the pieces where they disagree, which are here. You see, there's pieces where they don't agree, they don't go over each other. The pieces where they disagree are very small. And moreover, this gradient, which I said it was less or equal than 1, in fact is not. In fact, is actually really small, the L2 norm. And if you've done any measure theory, that tells you that when you apply Chebyshev on a large set, this gradient is very small. So this thing is looking really, really flat. Okay, so this is what it means to be, well, this is a special case of uniform rectifiability. What we have shown is that if you start in that funny class that I define, and you assume, you only assume, I mean, that's the key point from the GMT point. I only assume a small oscillation at one point, okay? At that one point. Then we're able to prove that in that neighborhood, in half of that neighborhood, you are a Lipschitz graph, except some little islands that you cannot control. Okay? Questions? Okay, so let me say a couple of things. As I said, this is something I learned from teaching the class about perimeter minimizers, and then we had to prove it. The other thing, one of the motivations was I have spent a lot of time trying to characterize, as I think I mentioned yesterday, the regularity of the domain in terms of the regularity of the solutions of the harmonic functions at the boundary. And these gave us, and so this is for just a few of you, this gave us the following type of characterization. Under some very mild hypothesis on the boundary, the unit normal is of bounded mean oscillation and small norm, or of vanishing mean oscillation, if and only if the logarithm of the Poisson kernel from the inside and the outside satisfies exactly the same hypothesis. So some of you might have heard that if you have a C1 alpha domain, the Poisson kernel, whatever that is for the others of you, is C alpha all the way to the boundary. And under some mild assumptions, this is an if and only if. This brings us down to the VMO realm. Okay, so this is a characterization of a non-smooth domain in non-smooth terms, but in an if and only if way. So that's one of the things we wanted to do. As I said, the other thing, the other motivation, I wish I could tell you anything about that, but that we're not there. The other motivation was we are studying problems that are not rotationally invariant, okay? And therefore, And there very little is known. So while perimeter minimizers have been understood for a while, when you take a functional that's anisotropic, I don't want to go into details, there very little is known. Basically, we are just at the place where we know that a minimizer exists and it's rectifiable, okay? I mean, if you want, it's a set of locally finite perimeter. And now we want to understand the regularity. And we're trying to find ways. And it's way harder. And so this approach was a first approach to show that at least that we have these for those. From there, when you have a minimizer, you want to improve things. But we're not sure how to do that. So I realized there's no way I can even state the beginning of the proof that I wanted to do, so that will have to be the material of another time. But what I wanted to say is I hope you got something out of the class, even if this was not your field and this was the first time that you encountered some of these words. I also hope that one of the things I would like you to take away with you is the fact that both teaching in class and taking a class can be very useful. If you think of it, some of these led to a paper from just a topics class. These led to a paper that involved graduate students, postdocs, and myself. And as I said, I believe at the beginning of the week, my work in the area that motivated some of this work started from me, already an assistant professor, sitting in the class to learn something else. So it's not only don't be afraid of learning something else, it's a very productive thing. And if it looks like you spent a year learning something else and you're not producing anything, it might be the most worthwhile investment of your career.